Okay. Hello, everyone. Okay, this video is homework problem. And this problem, yeah, maybe it's kind of difficult to you, okay, or this really takes you lots of time. So just just record this video to explain this homework problem to you, okay. Okay, so let's just see which problem. Okay, let's just see here. Okay, here is the homework problem 1070. Okay, say there is a shaft here, and this shaft is made of two parts. Okay, A B, then by two part. One is AB part, the other is BC part. AB part is a solid, and BC part is a coaxial part. Coaxial part means there is a core shell structure. The core is made of brass, and the shell is made of steel. And the AB is a solid section. So the all the material here is all steel. Okay, this made of this section. AB section is made of steel. Okay. Okay, so he said we apply a torque at C. Okay, we apply a torque 75 Newton meter. Okay, and then first of all, determine the angle of twist at C. Okay, so and this part just want to calculate the angle twist at C and with respect to A. Okay, so that means 5 CA, 5 CA. And after calculate the angle of twist of 5 CA and also compute the shear stress at in shear strain. Okay, so it's specifically called maximum shear stress. Okay, and maximum shear strain. But actually, if you have maximum shear stress, you will cause a maximum shear strain. So that just tell you, okay, just determine the maximum shear stress in the brass and steel. And the brass and steel, yeah, brass has two parts because this is a coaxial section, this is a solid section. So if we want to determine the maximum shear stress for the steel, you have to calculate the maximum shear stress at the solid part and the maximum shear stress at the maximum shear stress for steel in the BC part. So you have to compare the maximum shear stress on these two parts for steel. Okay, but for the brass, okay, you only have to calculate the surface at the surface of the brass. Okay, the maximum shear stress at the surface of the brass. Okay, so this problem, yeah, lots of things you have to calculate. So let's start. Let's start from beginning. Okay, and yeah, and this is I'm not sure you don't may notice this or not. This problem, it actually is also a statically indeterminate problem. I'm not sure you notice this or not. Okay, but here I need to my pad. I need to. First of all, I just draw the core shell structure here. Just make a note for the core shell structure. Oh, okay. So the core shell structure, let's just draw a simple picture of the core shell. Not core. This is really not really a circle. Okay, so it's core. So it's a core shell structure, and the radius here is what's the 25 millimeter. Okay, and this is 12.5 millimeter. Okay, so and the core is brass. Okay, the shell is a steel. Okay, this is a core shell structure in the BC section. Okay, first of all, okay, it said determine the angle of twist. Okay, at the C. So that means he want us to calculate the 5 CA. Okay, angle of twist of C with respect to A. Okay, so okay, because in this how to say because this bar had made of two sections, solid section and coaxial section, so the angle of twist intuitively, the angle of twist in BC section is different from the angle of twist in AB section. AB and BC section would have a different angle of twist. Okay, so actually, okay, we have to calculate the angle of twist of each section and add them together. That will be the angle of twist of C with respect to A. So I just write phi AB and plus phi BC. Okay. Okay, so how to calculate phi AB? Okay, phi AB, let us calculate phi AB. Okay, phi AB, what do we know? We need to know the torque at AB and the length of AB divided by GAB and JAB, right? GAB and JAB. And the torque of AB, how do we know the torque of AB? How do we know the torque of AB? Okay, actually, the torque of AB is very easy to calculate in this problem. So, okay, we need a torque of AB. So we just the cut section. Okay, we use the cut section. Okay, here cut section here, and we have external torque. Clockwise, right? Clockwise 75 Newton times per meter. So at the cut section here, we will have the unknown torque. I call it torque AB. Because I don't know its direction, I assume everything is counterclockwise. We have TAB here. Okay, so and the first 75. Okay, minus 70. Sorry, wrong color. So minus 75 plus TAB will become to 0. Okay, let's do a moment balance on the section. This cut section. So minus 75 plus TAB is equal to 0. So let's tell you TAB is 75. Okay, and the Newton times per meter. So in this problem, TAB. Yeah, just right here. TAB is just equal to the 75. Okay, Newton times the meter. Okay, and do we know the polar moment area of AB? And so let's see this problem. This problem give us information of the. Oh yeah, this problem gives us information of the radius of the radius of this section. The radius is 25 millimeter. Yeah, yeah, you have to check this graph very carefully. So the radius of core section of AB, the radius is 25 millimeter. So actually, we can find a JAB. Okay, we can find a JAB because this problem gives us a radius. So it's pi over 2 and 25 times the 10 to the power minus 3 to the power 4. And AB is a solid section. So there is no inner radius. We only have out radius. Okay, so we can have this value. Okay, so what's the value of this? Yeah, if you use a calculator, so that will be 6.1328 times to 10 to the power minus 7 and the unit n to the power 4. Okay, so we have everything here. So we have TAB. Okay, we just make a notice. JAB is 6.1328 times 10 to the power minus 7. Okay, so if you put this everything in there, so you have 75 and length AB is 0.9 and the G is, and this AB section is made of steel, so it's 75 gigapascal. So 75 times to the 10 to the power 9 and times the JAB 6.1328 times 10 to the power minus 7. So you have phi AB, you will find phi AB. So phi AB, you will have the phi AB. What's the value of this? Yeah, let me check my notes. Yeah, it's kind of a lot of things to do right now. Okay, so you will have. Let me check the number. So this phi AB is equal to 1.46752 times to 10 to the power minus 3. So this is the angle of twist for the AB section, and its unit is radians. Okay, so now we know the BC. Okay, the BC. The AB phi AB. Okay, and next part is to calculate the phi BC. Okay, so the phi BC. Okay, phi BC. Okay, phi BC. what do we have to know 5BC? First of all, we need to know the torque of the BC section. The torque of BC section. Okay, the torque of BC section. How to say this? Okay, so we need to know the torque. We need to find a torque at the BC section. Okay, yeah, we need to torque our BC section, and LBC and GBC and times the J, yeah, JBC, right? JBC. JBC. Okay. Okay. But that will face a problem. Okay. Because this is a core, because in BC section, this is a core shell section. So it's a core shell structure. Okay, actually, in previous video, I have recall one video for statically indeterminate problem for torque load member. So so it's very similar to this problem. Let's go back to see the PowerPoint here. Okay, and temporarily we close this off. I made a video for 10.9. Yeah, it's a coaxial structure. Okay, and this coaxial structure, the most important thing is, yeah, when you apply the torque on the coaxial structure, the core and shell, okay, the core and shell also share the torque. The core and shell are both share the applied torque. So that means there will be a torque. The torque will be contributed by brass, and there's a torque contributed by the steel. Okay, so back to this problem. Back to this homework problem. So here's the core shell structures. Okay, so this we apply the torque here, and the core and shell both share the applied torque. So for the torque, for the torque here, okay, if you want to calculate the angle of twist in this part, yeah, you need to know TBC, but which value you are going to take, because just like I said, the core part will contribute the torque, and the shell part also contribute the torque. So they both contribute the torque. So which value you are going to take? Yeah, that would be a problem. So for the deformation or the angle of twist on BC section, you cannot use this formula. To calculate the angle of twist for the BC section directly. So you have to use another method to calculate the torque at the BC section. Yeah, how to do that? Yeah, that's the difficult part for this problem. Okay, so we have to continue it. So for 5BC, I cannot use this formula, so I erase this out, erase this part, and I also erase this out because we finished the TAB calculation. I think we can ignore this part. Okay, so the next problem is how to find this, how to find a 5BC. Okay, so I also erase this part. Okay, and I just take a note here. Okay, I just take a note here. Okay, so yeah, I just erase this and take a note. Is phi AB is equal to 1.4675, 1.4675 times 10 to the power minus 3. Okay, let's just take a note here. Yeah, let's just ignore this. Okay, so let's take a note here. Okay, the next problem is how to calculate a 5BC. Yes, that's a very important part here. Okay, so how to calculate the angle of twist at 5BC? And because because this is a core shell structure. This is a core shell structure, and then this core and shell attach to each other. So actually, the 5BC in this part, okay, this one for this part 5. Let me see. I need a notation here. 5BC. Okay, actually 5BC BC part and steel equal to 5BC and the breast part. Okay, core. And this is for shield. This is for the core. Okay, yeah, because they are core shield structure. So when you apply a torque, they will share the same angle of twist. They have the same angle of twist. Yeah, it's very. Just think about yourself. Okay, I mentioned this before. Just I mentioned this problem before. Yeah, this problem is very similar to this example. Yeah, the core shell structure, they bound together, so they have share the same angle twist, just like this example. Okay, so back to this problem. Okay, so how to calculate this 5BC steel, 5BC and 5BC brass? Yeah, actually, this is you need to use the statistically indeterminate technique to find this value. Okay, so first of all, just like I said, we apply the torque here. Okay, and so we just mentioned that. Okay, in this core shell structure, uh, the core and shell both share the torque, share the torque, share or contribute to the torque. Okay, I should say both contribute to the torque. So we'll have the torque. Okay, so I need the torque BC, but it's from steel. And we also have torque in BC, but it's from brass. They both share torque, and this and the whole system on the whole system. Okay. So no, not whole system. Okay, and this torque applied torque. This applied torque. Okay, this is a torque. This is a torque from the core and shell structure, and we add the external torque. So this is a clockwise. So it's minus 75 equal to 0. Okay, this is rigid body equilibrium. The summation of moment or torque is equal to 0. Okay, it's rigid body equilibrium. So we will have the BC part, the torque from BC part, the torque from steel, and the torque from the brass. Okay, add together equal to 75. Okay, and and then we will have this condition, and then we use this both condition. We use this condition, and I'm sorry, we use this. No, sorry, we use this equation. It's not deep enough. We use this equation and this equation, and then we can solve the 5BC. Okay, how? Yeah, it's really a magic. Okay, so let's focus on these two equations. Okay, we'll focus on these two equations. Okay, so let's extend this equation here. Okay, 5BCST equal to 5BCBR. Okay, do you know, remember the formula for the angle of twist? So that means we need the TBC ST times LBC divided by GBC steel times the JBC but steel. Okay, and then equal to TBC but from brass. Is this okay? Maybe I make a connection here. Okay, big brass and the LBC and the GBC, but it's brass, and times the JBC, but it's from brass. Okay, and it's very lucky because they both at this core shear structure, so they share the same length of BC. So we can divide it. Okay, cancel this out. Okay, and TBC, ST, TBC, BR, yeah, that's we don't know, and that's we want to kind of want to solve. Okay, so first, and now connecting, do we know the GBC for ST and GBC for BR? Of course, it tells us the GBC ST because steel, so it's 75 gigapar. And GBC, but its breast part, the breast part is 39 gigapar. So yeah, we already know this. And do we know JBC ST and JBC BR? Okay, so let's see JBC ST still. Okay, this section and the steel is a shell part. It's a shell part. So, and we know the diameter. So how to calculate the polar moment of inertia for the shell part? Okay, so how to do that? And in this problem give us radius. Okay, so it's pi over 2. Okay, 25 times 10 to the power minus 3 to the power 4 minus inner radius times 10 to the power minus 3 power 4, and yeah, spread together. So what's the value of this? So I just tell you the value. Okay, we don't have to have much time. Okay, so it's 5.7495 times 10 to the power minus 7. And what is the polar of moment of polar moment of area of the breast part, or the core part? And because the core is just a circular, so there is no inner radius, so we just use a pi over 2, and the radius of the breast part is 20.5 12 times 10 to the power minus 3 and to the power 4. So what's the value of this? So I just give you the value directly. My result is 3.833 times 10 to the power minus 8. Yeah, check it by yourself. Okay, so and then we already know the GST, the shear modulus for steel and shear modulus for brass. So we can put some number here. Okay, so after all, we will have the equation like this. Okay, maybe right here. So we have TBC ST and okay, equal to TBCBR, and the steel is 75 times 10 to the power 9, and the J steel is 5.7495 times 10 to the power minus 7, equal to, yeah, I don't have any space here, so yeah, this problem is going to take some time. So, and we have TBC and the breast, and the shear modulus is TBC breast is 39 10 to the power 9, and times yeah, what's the JBCA here? So it's 3.833 times 10 to the power minus 8. Okay, so and then you can calculate this value by yourself. So finally you'll reach this conclusion. Okay, so you'll reach a conclusion like the okay, so you have to conclude TBC and steel is equal to 29.605 TBC and BR. Okay, so you use this comparativity equation, and then you get the relation between the TBC, this in the torque at BC section, and you know the ratio of the torque in the steel section and the brass section. Okay, and then you put this back into your equation. So you can solve that, okay, because we have two unknowns and two equations, and it's very easy to solve, right? These two equations combined together, easy to solve. Okay, so after all, so you have TBC still is equal to, and just give you the value, check by yourself. So it's 72.5494. And I just write here. Okay, maybe I just write here. Okay, so I don't really have any space right now. Okay, maybe I change that card. So and then you have T, B, C, and breast. What's the value? Because it's add together is 75. So the remaining part is 2.4506. Okay, so I think I need to make some notes here. Where is the empty space I have? Yeah. Okay. I just make a note here. Okay. So we have TBC steel, PBC steel, and steel 72.5494, and the TBC from the brass, what's the value is 2.4506. Okay, we take lots of effort to solve the TBCST and TBCBR. Okay, so what's the purpose? All the purpose, don't forget, we need to know the 5BC. Okay, 5BC. So actually from this equation, you know that, okay, we can use this to calculate 5BC, and we can also use to calculate the 5BC because the value will be the same. The value will be the same. Okay, you can take this to calculate 5BC or take this to calculate 5BC. No matter which you use, you will get the same answer. You will get the same 5BC. Okay, so I choose the 5BCST. Okay, I use this calculate value to calculate 5BCST. So what is a 5BCST? Okay, so I just erase this part. Okay, if you want to take a note, please rewind. Okay. Okay, what about 5BCST? Okay, I think you already know. I think you can see the answer. Okay, 5BCST, we just list the equation here. Okay, 5BCST. Okay, we need to talk BCST. Talk BCST, yeah, here. 72.5494. Okay, LBC, yeah, we ran this time. I don't have to cancel it out because we use this formula to calculate 5BC. So LBC, LBC is 0.6. And the GJ, okay, GBCST is still, so it's 75 times 10 to the power 9. And what is JBCST here? 5.7494, 5.7495 times 10 to the power minus 7. So after all, what's the value of this? Yeah, what's the value of this? So you will get this value is 1.00947 10 to the power minus 3. Okay, so this is your 5BC. This is your 5BC. And we already got a 5AB, right? We already got a 5AB. So finally, what's our 5AC or called 5CA? You just add these two together. You just add these two values together and this value together. That's our 5CA. So you will get the answer is 2.477 times the 10 to the power minus 3, and the unit is radian. Okay, so that's the first answer for this problem. Yeah, it's really take lots of time. Okay, it's really take lots of time. Okay, so that's the first part of this problem. Okay, 5AC, and but we haven't finished yet because in the second part, I want us to compare the maximum shear stress. Yeah, I also want to compare maximum shear strength, but actually that's maximum. The main point is maximum shear stress because you have maximum shear stress, you know the maximum shear strength. Okay, so next part is what is the maximum shear stress at the breast part and steel part. Okay, and this video is kind of too long, so I will finish the second part in the next video. Okay, you can take a breath. Okay, so see you in the next video. Okay, bye bye. Okay, bye bye. Oh.